Hello and welcome to our overview about NoSQL databases and MongoDB. My name is Philipp Brune of the Neu-Ulm University of Applied Sciences. When we look at the history of database management systems, we see that nowadays and for many years, even decades now, relational database management systems, or RDBMS, are the dominant technology for business and enterprise applications. The success of RDBMS is also due to their simple concept and principle. The simplicity of the concept of the relational model that allows, with a single concept, namely the relation, or as we typically call it in practice, a table, to model basically all kind of data structures. Is a very conceptually very simple and very powerful idea proposed by Cott in the 70s already. And since then, database management systems that use that concept of relations became very successful because despite that the basic idea is simple, these tools are very, very powerful, and a lot of programming features could be added to the systems, and this made these database management systems complex. But most of the central data stores like DB2 or Oracle DBMS in companies, also on the mainframe, or typically on the mainframe, are RDBMS today. RDBMS support transactions very well since they run on vertically scalable systems. And due to the standardized language, SQL is query language, standard query language, structured query language, which allows to access the data in a standardized and platform-independent way, at least in theory, platform-independent way, makes these kind of databases very, very nicely to use, and so they are used more or less in most classical business applications today. Nevertheless, there are scenarios where RDBMS may not be the best choice or the best tool, or even are not capable of handling certain types of data. And in recent years, with the rise of the internet and all these heterogeneous data, NoSQL databases showed up. NoSQL is an acronym that stands for not only SQL, so they are not meant as a replacement for RDBMS, which are very good for a lot of scenarios in corporate and enterprise computing where you have structured, well-structured information, but NoSQL focuses on another domain, namely the data processing challenges that arise from big data processing, from analytical processing, from using heterogeneous high-volume data that is not so structured. For example, if you think of data in the internet, you might have videos, audio files. These are very, very poorly structured information. We have geospatial data. We have the social graph in social networks. Social graph means the network that is you and your friends and the friends of your friends and the relations between them, which are graph-like structures. So that's the social graph, which can become very big. And all this kind of information or textual data, just plain text, natural language, all these things are informations that we have nowadays more and more. And when we talk about big data, we see that the majority of the data in the world is unstructured and heterogeneous and not structured. So for these kind of data and for the analytics and the artificial intelligence and machine learning and so on, we need another way of storing and retrieving this information. And this is where NoSQL comes into play. So it's not a replacement for the classical RDBMS, but an addition, alternative approach. And typically for NoSQL databases is that they don't use very strict structures. They can store information that is different, that is not structured with the same structure like in a table, for example. And they focus on a distributed processing. To process these large amounts of high volume data and fast process this data, NoSQL databases typically focus on a distributed processing scheme running on nodes in a cluster or in a grid. So the processing is split up among separate nodes that are horizontally scalable. Scale out is the topic here. And these different nodes are connected to each other using a network and exchange data using the network. And therefore, these databases need to ensure schemes that allow distributed processing. And availability, the high availability, is typically achieved by redundancy and by replication of data. And this whole databases are, from the idea, from the origin, they are horizontally scalable. Typically, this is achieved by avoiding having strict schema, so they are schema-less, having simple, efficient APIs, like, for example, JavaScript-based or RESTful APIs, and by usually dropping the support for strict transaction properties, the ACID properties. This was more or less one of the typical domains of the RDBMS systems, or is still, since transaction processing is an important concept. We learned that in the chapter about transaction processing. And relational database management systems are rather good in ensuring the transaction properties, the ACID properties, and having transaction-aware processing. Of course, this requires, or this limits the processing to a single machine, which is what we call the vertical scalability, and which is typical of the traditional mainframes. And in NoSQL, we have the different scheme. They are horizontally scalable, and that is very different and very difficult to achieve these transactional properties. So typically, NoSQL databases either provide no or just reduced guarantees for the ensuring the ACID properties. So these are typical concepts that are common to nearly all NoSQL databases. And one sees that it's not about replacing completely RDBMS, but providing tools for different kind of workloads and for different kind of application scenarios. NoSQL is more like a general term. So behind the idea of NoSQL, there are different types of database management systems and different types of solutions that implement these kind of schemes. And on this slide, you see sort of a list of these typical NoSQL classes, or this classification of NoSQL databases. The topmost is the so-called key value store, or sometimes also called tuple store, which is the most classical NoSQL database type, probably. Then we have document-oriented databases, or document stores, and column-oriented databases. There are some more which are in principle fall in the category of NoSQL, like the graph-oriented and the object-oriented DBMS. But these two are somehow NoSQL databases that are already existed already before the hype and the discussion about NoSQL. So I put them in brackets here. We will not discuss them further because these existed already before the NoSQL discussion. And graph-oriented database management systems are those that use a graph, so a hierarchy or a network-like structure to store and retrieve the data. And object-oriented database management systems, or ODBMS, exist already from the 90s. It was a big trend in the 90s. In research and also in practice, to extend relational models to object-oriented models. But this trend more or less did not lead to a replacement of RDBMS. Instead, the mainstream RDBMS systems like DB2 and Oracle have been sort of enriched by object-oriented features. And on the other hand, the concepts of object-oriented databases like object-oriented query languages more or less lead to the evolution of these object relational mapping libraries like Hibernate or JPA that we, for example, have in object-oriented languages, which are not really independent databases but map object-oriented structures in programming languages on the relational tables and providing an object-oriented view on the database. So the concepts are there, but these kind of databases are a bit special and do not play such a big role anymore today. So we will not further discuss graph-oriented and object-oriented databases in this lesson. Okay. So let us have a closer look on the typical NoSQL data stores like the key value store in the following. So let's have a short look on the first three of the list because they are typical for the different solutions, the different database systems that exist, most of them open source implementations. So let's start with the key value store or tuple store. In a key value store, basically an object, a data set, any kind of data, we call it the value, is stored, referenced by a key. The key can be a number or any kind of unique and identifier that references the data that is the value. Okay, so you can see it here. We have a key, and on the other side, the key points to some kind of data. The data can be different for each key. It's just sort of a unstructured thing. Okay, and this is of course very efficient if you want to store heterogeneous data and you want to access it only by means of the key. So in a key value store, the data can only be retrieved by the key. It can be searched via the key, but it cannot be searched by the content in the object. This is on one hand very simple, on the other hand rather powerful, because in many applications you typically access the data by the key. Just think of business applications where you, for example, work with customer data, always going in with the customer number or with a building number or things like that. In general, this idea is not new. It exists for many years. For example, there is for decades now on Unix and Linux systems, there is BerkeleyDB. BerkeleyDB is a key value store implementation, now belongs to Oracle. It's an open source database, more like it's written in C. It's a small library that's very efficient to store and retrieve data and can be used in other applications, for example. More closer to NoSQL typically are databases like Membase, Couchbase, or Microsoft Azure Cloud provides the so-called table storage, which is a key value store, and there's by VMware the Redis database. So these are open source databases that you might know and that are used, for example, in the web development or application development and other things in the context of big data applications. In general, you can think of a key value store similar to a hash table or hash map in Java or in any other higher programming language where you can reference a data object with a key. Okay. And there's also a relation to the mainframe because on the mainframe we had also key value stores already a long time ago in the so-called ISAM or VSAM datasets, which provide this kind of index sequential or key sequential access that is basically nothing else than a key value store. So these old ideas, they still are alive and useful, and you see that many of these old ideas come back in a new dressing today. So they have proven to be valuable over the years. A variant of the key value store is the document store, and this is probably the most popular type of NoSQL database. The document store or document-oriented DBMS works in a way that the data that is stored under the key is not just undefined data, but it's a document. And the document has a structure, typically a hierarchical structure. And the documents are referenced by a key. The key points to the document, as you can see here. But the document now may be a JSON structure or it may be a XML structure, typically. And every document can be different, so there's no fixed schema like in a relational database. But the objects have a structure, and a structure makes it possible to search and retrieve data according to the content of the document as well. So in these types of database systems, they are rather similar to key value stores, but the document has a structure, and therefore it's searchable and retrievable using query languages that work on documents like XQuery, XPath, and JSON-IQ. The most popular formats that are used in this type of documents, document-oriented databases, are either JSON, the JavaScript object notation format, which is a textual representation of hierarchical information in a way that it automatically is a valid JavaScript object definition, so it can be directly parsed and used in JavaScript, which is very nicely for building web applications that directly access the database from the front end. Or it is XML, where you have the typical tags with the brackets and a structure that is also a hierarchical, self-describing document structure. Examples for these kind of databases are, for example, BaseX, which is an XML-based database, or Apache CouchDB, which is JSON-based, or, of course, the most popular one that we will have a closer look on afterwards is a MongoDB. MongoDB is probably the most popular NoSQL database, nowadays used in many types of applications, also business applications, and it's JSON-based, so it's a JavaScript-oriented database. Another type of NoSQL databases are the so-called column-oriented databases, which are again similar in some way to key-value stores, but they use combined keys consisting of a set of column table or column values. You can think of column values, and this can be, so it's a multidimensional key. It can be rather complex. It can have a lot of components, and all these components together, this set of values, identifies then uniquely, for example, a document like an HTML page. That is where it's already coming from. Then it was invented by Google, basically, to store and retrieve the pages in the search engine. Okay, and that was the original publication by Chang from 2006, and then the idea is that again, this is not so strict as relational models, since we do not have to have a value for every column in one key. So the key can also just have empty fields, and therefore it's not directly comparable to a set of columns in a relational database. But it provides the concept to store the data, not row-wise but column-wise, in a sense that you can have also compression techniques to reduce the number of values. For example, if the same value comes many times in the column, one after another. Okay. Examples for this kind of databases are, for example, HBase, based on the Apache Hadoop file system, distributed file system, and of course Google Bigtable, which is also used in the Google App Engine. And this is due to the fact that Google basically invented this kind of databases. And there's Apache Cassandra, which is also very popular. It's also an Apache project, and Cassandra is again such a multi-column database, also schema-less, and also a typical NoSQL database. Cassandra is written in Java, and therefore it runs also on the mainframe, for example, even though there are some pitfalls when porting Cassandra to Linux on the mainframe. We tried this once. We experienced some problems, since somewhere in the jar files of Cassandra there was some C code hidden that had to be compiled first, but afterwards it worked. So Cassandra is ported and portable also to Linux on the mainframe. But what it tells you is that sometimes porting even of Java applications can be cumbersome because there are some hidden native code parts. And also Hypertable is another example of such kind of databases. Let us have a closer look now on MongoDB, since it is probably the most popular NoSQL database. And when we discuss about NoSQL databases in general, one has also to talk a little bit about MapReduce. MapReduce is more or less the fundamental principle that basically all these distributed NoSQL databases use to process or to do data processing, complex queries on distributed data. As I said, the one common concept of NoSQL is that typically these databases are made for running on a grid or a cluster of nodes of servers, which means that one has to find a way to distribute the work, let the work be distributed, and collect again the results. So you have again a common central point of accessing the data. Okay, and this is what the MapReduce scheme is basically made for. And it was introduced by Dean and Gemawat in 2004, proposed in a paper by Google, and it's basically implemented in all NoSQL databases today. And the basic idea is always you have a structure like this. There's a master node, which is responsible for the interaction with the client, with the user, or with the software that uses the database. And then it gets a query, for example. It distributes the work on the so-called worker nodes. You must imagine that this usually involves a network communication here to the different nodes. The worker nodes process part of the data. The data is gathered again in the master node and maybe then distributed again for the next step. So there's always network communication involved in these kind of distributed architectures. And the MapReduce scheme is designed in a way that you split up every data processing operation into steps, the map phase and the reduce phase. In the map phase, you can see how it works. A mapping is done, and it is a mapping that for each key value pair that is processed, this is mapped to a list of another set of key value pairs. Okay, and you can imagine this. This is the example from the paper here, which is basically talking about documents. Think of the question: you want to count the words in a big set of documents, of text documents. And you split the text document on the different worker nodes, and every worker node first starts to count the words that he has in his text or in its text on the node, and you get a list of words and the number of occurrences. So this is the key value set. And then the data is collected and distributed again, which is called the shuffle phase, which is always between the map and the reduce phase. And then the second step now, the nodes start to aggregate for each different key the counts that they have been obtained in the first iteration. Okay, so that is the basic structure. In the first step, first it is mapped and then it is summed up and aggregated. And this is basically the fundamental scheme, and a lot of data processing operations can be somehow mapped on this kind of scheme. Of course, the function that is actually executed in the map and in the reduce phase is sort of specific for every single query, or has to be provided by the developer for every operation separately. So it's not a given, it's more like the scheme how it is executed. And MapReduce is the underlying scheme for most of these relational database, non-relational databases, these NoSQL databases. And of course, MongoDB runs on Linux, and it runs on Linux for System Z, not from the beginning, but for some years now. It has been ported. MongoDB is written in C, and it has some internal dependencies in the original version on the x86 architecture and the register structure and things like that had to be modified for the port. So it was not something that was ported immediately, very early, but it is available now for some years already. So MongoDB is a database to store JSON documents, as I already mentioned, and I wanted to illustrate this. So you see some screenshots here on the right-hand side. The screenshot in the background is basically to illustrate and to prove to you that we are really working on a mainframe. So you see this is our Linux prompt here, and I just printed out the info from CPU info from the proc file system, and it shows you that it's S390 architecture here. So you see it's on the mainframe. You can see the prompt, and it's the same here. So you hopefully believe me that this has been run on a Linux on the mainframe, because otherwise you won't recognize, because MongoDB on Linux on the mainframe looks basically the same as MongoDB on every other Linux version. Okay, so on the right hand side, so you see an interaction with the MongoDB from the command line. So this is a command line tool, Mongo. It's a client that has an interactive shell where you can give commands to the MongoDB server. And here are some status messages, but then we start to to illustrate how it works. So you see here the demo dataset, and a dataset is added, or document is added here to the dataset. We add a character from Harry Potter here in the dataset, and you see it's just a JSON object. You can see the JSON object here, consisting of names and values. And it is just put inside the dataset with this JavaScript style notation here. So basically the interface is also, it looks like JavaScript functions. And then in the next step, there's a query executed. The query is executed by just putting another JSON object that sort of classifies the set of objects that should be retrieved. So everything with a certain value for occupation is retrieved, and then we get the results here. Okay, so they are printed out. What you can see is that here we add the data set, and here you see that it adds the key. So the key is this technical identifier that you can see here, the ID, which is automatically created then for every document that is stored in the database. So this works on Linux on system set, and the question, of course, is this useful, or why we do that? And again, the mainframe is not a distributed architecture. So a MongoDB instance on a Linux for system set does not necessarily have to use the distributed and horizontal scaling mechanisms of MongoDB. So either you can now put MongoDB on a virtual cluster that runs on a single machine of virtual Linux guests, for example, on a mainframe. Or you can just use vertical scaling and just run it on a single node and make this node very big. So both options are possible. In both cases, you may reduce the overhead for administration and network communication compared to the installation in a distributed network cluster. So it has some advantages. And in combination with the I/O bandwidth and the data processing capabilities of the mainframe architecture, this can lead to very powerful and very efficiently administratable MongoDB instances. So this was what I wanted to present about in NoSQL in general and MongoDB in particular. There's the most prominent example probably. And we say that these modern concepts of NoSQL also play a role in the mainframe world, especially on Linux for system set or Linux One. Thank you very much.